So the idea is, really does, if we get a sample and we get its mean of my sample, does that tell me anything about the mean of my population? Well, it does. And what it gives me is it gives me an interval in which the population mean should lie. So I get my sample, from that I can get an interval, and then I'm pretty sure, not 100% sure, but pretty sure that my population is in that interval. And we'll see why that's the case. So for one sample, so if I go through and do a sample and I get its mean, here I've got the distribution of sample means. In other words, this is a normal distribution and this is all my different sample means. The mean of my means is mu. And the standard deviation is the standard deviation of the original distribution divided by the square root of n. Now, I can put, say, 2 vertical lines there, and I can colour in this area. And what I'm going to say is that this is 95% of my area. So, 95% of my sample means are in this area. Which means that for one sample mean, for my one sample mean, there is a 95% chance it is in here. I cannot guarantee that my sample mean is in this region. I'm only 95% sure that it's in that region. Now, this sample mean, though, has a z-score. What's the z-score of any value? What's the formula for the z-score of a value? Z equals what? So it's a value, take the mean on the standard deviation. So, for my sample mean, well, I'm going to call my sample mean x bar, then its z value will be x bar, the sample mean. Take the mean of this distribution here, which is just mu, divided by the standard deviation, which is sigma on root n. That's the z-score corresponding to my sample mean. It's the value of the sample mean, take the mean of the distribution, which we get straight from there, divided by the standard deviation of that distribution. You also get from that. This is coming out of the central limit theorem. Now, what I can do is I can say, well, there must be 2 values, and they should be in the same position, so I'm going to have to take that out. It'll line up on yours, but it doesn't on mine, because OneNote is going spastic on me. So there will be two values on my Z distribution in the same, and it will look like it's in the same spot as it was on the original distribution, between which 95% of my area under the normal distribution gets captured. So we're 95% confident that the Z score of this sample mean is between these two values, because we were 95% confident that the sample mean was between these two values here. And so these two values, these two ends, correspond to these two ends on the Z distribution. Now, what are these two numbers? That's the question we're going to ask ourselves. Well, the calculator can give them to us. So I want everybody to get out their calculator. And I want you to go to statistics. And we'll take a distribution and we'll go to normal. And we're going to do an inverse normal because we've got an area, but we want to find a value. But instead of having our tail as left or right, there's a third option which is central, which means that we want our area centered on the mean and an equal distance either side of our mean. So the area that I had was 95% or 0.95. And we're working in the Z distribution, so it's got a standard deviation of 1 and a mean of 0. So what value do I get or what are my two values on either side of 0 that gives me my balance, my 95% area? And negative 1.96 on the left, 1.96 on the right. Yep. So we're 95% confident that our Z score of the sample mean is between negative 1.96 and 1.96. So what I can do is I can say that Z, where Z is the Z score of my sample mean, is less than or equal to 1.96 or more than negative 1.96. Now we're 95% confident about this, which means that I can then say that my sample mean, take mu, all over sigma on root n, is between those two values. All I've done is I've substituted the value for Z, the formula for Z, in place of Z. Now, as I can do with an equation, so I can do with an equality, I can multiply everything by this sigma on root n. So I get negative 1.96 times sigma on root n is less than or equal to x bar take mu, which is less than or equal to 1.96 times sigma on root n. When I multiply this middle term by sigma on root n, it cancels. So it's not there anymore. And so then I can subtract x bar from all sides. So it's going to be negative 1.96 sigma on root n, take x bar, less than or equal to negative mu, which is less than or equal to 1.96 sigma on root n, take x bar. Here, by subtracting x bar, I've got rid of it, and so then it's just on either side. Now I've got to divide through by minus 1 because I just want mu. Negative mu isn't really any use to me. So dividing by minus 1, what happens to inequality signs when we divide by a negative number? They get flipped, so we're going to have to flip them. So when I divide all of this by a negative number, I'm just going to get a positive number. So it's going to be 1.96 sigma on root n plus x bar is greater than or equal to mu, which is greater than or equal to negative 1.96 sigma on root n plus x bar. Now, if I say 5 is greater than or equal to x, which is greater than or equal to 3, let's say x is 4, do you agree that I can say that 3 is less than or equal to x, which is less than or equal to 5? I can swap the signs and reverse the ends without actually changing the meaning of the statement. So this says that 5 is more than x, which is more than 3, so x is 4. This says 3 is less than x, which is less than 5. Either statement is true for x being 4. So we're going to do this. So I'm going to bring this bound to the other end and this one over to the other side. So I'm going to swap the two ends and also change the sign. So mu is going to be x bar, take 1.96 sigma on root n. That's going to be less than or equal to mu, which is going to be less than or equal to x bar plus 1.96 sigma on root n. All I've done is I've taken that statement, swapped the ends and swapped the signs. Without actually changing the meaning. Anybody want to argue with me about that one? Okay. Now notice this mu is my original distribution. That's the mean of my original distribution. So I know for mostly, not absolutely confident, but pretty confident, that it's between this value and this value. Provided that I know that the sample mean, my sample size, and my standard deviation of the original distribution, I can go through and find bounds on what the population of the distribution should be. So we can say, now remember, when I got this value of 1.96, and at the start, I was only 95% sure that the sample mean fell in this area. So I'm not 100% confident it's between these two values. I'm only 95% confident. But we can say that we are 95% confident that the population mean mu is in the following interval. That interval being from x bar, take 1.96 sigma on root n, and x bar plus 1.96 sigma on root n. Who'd be happy with being 95% confident of that? Who thinks 95% confidence, pretty reasonable? Any support for a group? Yes, we got 2 people. So out of all the people left, what would you say is more confident? What percentage do we need to go to be more confident? Yeah. 99.95%. Marcus, what do you reckon? 99.7%? Now, the more confident that we are, the more area we're going to have to capture of this normal distribution. So I'm never going to be able to get 100% because I'm going to have to go from negative infinity to infinity to get 100% of this area. So we can never get 100% area because that goes from negative infinity to infinity. But we can, we'll go with 99% area or any area really. So that our percentage confidence will determine our value for K. So all I've done is because 1.96 was dependent on the 95%, if I want a different percentage, I'm going to have a different value there. So I'm just calling it K for the moment. And how do we get K? Well, K is given by the central inverse normal on the calculator. And we'll see plenty of examples where we calculate a different K. Now I'm going to skip over this little bit. This goes through how to find it on your calculator, but we don't really have a practical example yet. So we'll move on from that and come back to that in a little while. But if we want to think about how the confidence intervals behave, but first of all, what does a 95% confidence interval mean? This is rehashing what we've talked about. So from the point of view of a single sample, if we take one sample and find its mean, which is x bar, and based on sigma, we calculate an interval, then we are 95% confident that it contains the population mean. Mu. That's what it means. One sample used to calculate our interval, 95% sure that it contains the population mean. So how do confidence intervals behave? Well, they have two aspects which kind of play off against each other. First one is the level of confidence. We want to be confident that it's in there. But you see, the other thing is the width of the interval is also important as well. See, if you have an interval that goes from 1,000 to 10,000, that doesn't tell you very much about the population mean. So a really wide interval doesn't really help us. So whoever's coming up with the population or with the interval chooses the confidence level. And the width of the interval is then set by your confidence. So the width of the interval follows this choice. So the best scenario would be to be really confident and have a narrow width, but it can't work that way. As soon as you've chosen the confidence level, you've decided on the width. So, high confidence is desirable. But so is a short interval, because you can say more about the population mean. So if we've got high confidence, then that means the interval is almost always capturing the population mean. If we've got a short interval, says we have a good idea of mu, so we're going to know a fair bit about the population mean with a small margin of error. So both are useful. High confidence means we can almost always be certain it's in there, it's actually in that interval. And a short interval says then we have a pretty good idea about it. So there's a trade-off. Between confidence level and the width of the interval. So if we want to increase confidence, so to obtain a higher confidence, then we're going to have to accept a greater width. And vice versa, if we're going to, well, there's only one other way to ensure that we can narrow width without changing confidence. And that's actually by increasing the sample size n. Because that's going to narrow the width. For any fixed confidence. You see, the larger sample you take, the better the mean of that sample is going to approximate the population mean. You see, if you think about it, if your sample size is getting closer and closer to the actual full population, then the mean is going to be a better approximation for that population mean. Okay. So let's go back to our distribution of rainfall per month in Golden Grove. That's what we had a look at when we started continuous random variables. Now I've taken I've got the population and I've worked out its mean and standard deviation. Its mean is 50.2 and its standard deviation is 35.2. This is the X distribution, this is the X bar, this is our distribution of means of size 20. So if I find a value of 20, if I find a sample of 20 and find its mean, then I can get a confidence interval around that. So 50.53. Let's see how we actually get our confidence interval. We're going to need to know that the standard deviation is 35.2 and our sample size is 20. So on your calculators, we need to exit out of this, and instead of going to a distribution, you'll see that F4 represents an interval. And we want a Z interval, because this is based on the normal distribution. T represents a different distribution that we don't come across. So that's never going to be used. Now you'll see there's a 1 sample, 2 sample, 1 proportion and 2 proportions. We're only ever focusing on a 1 sample and a 1 proportion. But because we're talking about samples, it'll be a 1 sample. The confidence level of this interval we're going to say is 95%. The standard deviation, I can't actually remember, what was that? 35.2. What was our sample mean that we're working out for? Sorry. 51.53. And our sample size is 20. Go through and execute that. We get an interval that says we're between 36.1 and 67.0. So this is 95% between 36.1 Notice, when I write my interval, it's mu that's in the middle there. A lot of students don't really understand what they put in the middle, so they might put X bar. And you'll lose a mark in a test or exam for putting X bar there. Has to be mu. Because this is an interval on the population mean. It tells us we don't care about the sample mean. We know what the sample mean is. We calculated that. This is an interval on the population mean. Okay, I want you to go through and do it for 38.46 and for 68.89. Calculate those intervals.